This is the last section in this chapter. It's section 4.5, and we're going to talk about modeling with exponentials and logs. Okay, and these fall in a couple of big categories. Exponential growth. And exponential growth occurs when you're multiplying by the same number or approximately the same number at each step. Now what separates these from the linears is that at linear you're adding the same number at each step. With exponential growth, you're multiplying by the same number at each step. Decay, or exponential decay, is very similar. Except you're dividing by the same number. Or you're multiplying by a number which is less than 1. It's a fraction. Okay, so let's look at some potential looks at these things and applications. The first obvious application is populations. And here we tend to be talking about some kind of a biological population. These things are usually modeled by some kind of a exponential function. And we're going to talk about a little later on about how we can modify these things. But for right now, let's just talk about general growth. And for populations, we tend to talk about the population at some time t is going to equal to your initial population, which is p sub 0, times e to the rt. And this looks like continuously compounded interest. And it's because it is. Remember, continuous compounded interest was A equals P e to the RT, where P was your principal. It's what you can think of as your initial investment. This is the amount of money. This is going to be population at time t. Now, you can use this for either growth or decay of populations on either one. For decay, R would be negative. For growth, R would be positive. And let's take a look at an example of how this can be done. Okay. So what we do is we have a population whose growth rate is 3% per year. This is a real good indication. This growth rate at 3% per year is a good indication of exponential growth. We start with 100 million of whatever these guys were, and we want to find the population in 20 years. Okay, so the first thing I do then is I come back in. I know I'm going to be dealing with this equation right here. So P of 20, because that's the time we're interested in. Okay. This right here is my t. Right here, r is a decimal, so it's going to be 0.03. And this right here is my p sub 0. So p sub 20 will equal to p sub 0, which is 100 million. I'm going to leave the million off for now, and I'll put it in at the end in my population, times e to my rate, which is 0.03, times t. All right, this is an exponential equation. Go back to the last one. If you remember right, what we said was in order to solve this, the first thing we have to do is isolate my exponential on the left. So I'm going to move my exponential over. Oh, no, wait. What am I doing? Thinking ahead. I got 0.3, and then I know my t, which is 20. So at this point, this just becomes a matter of plugging this into the calculator. So if you plug this in, you end up with 182.2. But remember, my initial population's in millions, so this will be in million critters. Okay, so this is a rather straightforward way of going in and solving and getting a population. You have to be real careful when you use this, because at long time periods, your population gets very big very quickly, and so you really do not use this type of equation to predict very far ahead. We tend to use what's called a logistic equation, which is modified from this one. Okay, so let's come back in then and look at a slightly more complicated one. What we want to do is, we know that in 1900, the population was 12 million. In 1990, it was 15 million. Find an equation to model growth, to model population for years after 1900, which will be when t equals 0. Okay, now what we notice here is, unlike this other one, we weren't actually given a rate. We're just given the population at 2 different times. So what we're going to have to do is use that to find our rate. And I'm going to show you how to do that. So first of all, let's go in and get some things. We know p sub 0 is going to equal to, that's what we started with, and that's our 1900 population, and that was 12 million. And then we know p of 90 years after 1900, so it's going to be p of 90, was 15 million. And we know t is 90. So if we come back in and take a look at this, what we're missing is r. And this is where we actually have to come back through and solve for it. So let's go in then and take a look at this guy. So we're going to plug back in so I know, if you remember right, the equation was P of t equals P0 e to the RT. So I'm going to have 15 equals 12 times e to the 90r. I plugged in 90 for t. All right, and we need to get rid of this. This is solving the exponential equation. So first thing I need to do is isolate it. So I'm going to divide by 12, which will give me 5/4 equals e to the 90r. Okay, if you remember from solving exponentials, the next thing I do is take a log. So this is base e. I'm going to be dealing with natural log of 5/4 equal natural log of e to the 90r, or natural log of 5 minus natural log of 4, using my log laws, will be equal to 90r, or r will equal to natural log of 5 minus natural log of 4. And then I take that difference and divide by 4. So now this becomes a calculator problem. And r comes out to be about 0.014, or we're growing at 1.4% per year. Okay, so now we've got our r. We can actually come back in now. There we're looking for an equation. So P of t, where t is in years after 1990, will be equal to P sub 0, which was 12, times e to the 0.014 t. And so now if you want to find the population, or at least what it predicted to have been in 2012, then t would be 112 years, and you plug it in and calculate it. Okay, let's go off to another type of problem. And this is radioactive decay. And radioactive decay is an exponential decay. So this is going to look very similar to what we have. All right. And we're going to be dealing with the same basic thing, but where the amount of material left at time t is going to be equal to what I started with. And again, it's e to the RT. R is going to be negative. Okay, so let's take a look at an example of these kind of things. What we know is the half-life of carbon-14 is about 5,730 years. Now, half-life is basically the time that it takes for half of your radioactive isotope to decay. Okay? And I'm going to show you how to convert that into a rate. The sample we have contains about 65% of the original carbon-14. And this is usually the data we get out of carbon-14 dating machines. Okay. So what we need to do here then, but you notice we don't really have P0 or P of T. However, this 65% tells me that P of T divided by my original will be 0.65. All right? So let's come back in and take a look at this guy. So we can solve this, and we're going to have to get it exponential anyway, over P0 equals e to the RT. Okay, well this is pretty neat. But we're still not any closer to actually getting it because we don't know, and we're solving for age. Which will be T. So what we do know, though, is the half-life. And half-life, if you remember, means that half of it's left. So this ratio will be 1/2, will be equal to E. And the half-life was 5,730 years times R. And then we solve for R. So we're going to have natural log of 1/2 equals natural log of e to the 5,730 R, or natural log of 1 minus natural log of 2 will be 5,730 R. Solve for R will be equal to natural log of 1 minus natural log of 2 divided by 5,730, or R is going to be approximately equal to negative 0.00012. And this should be a negative for radioactive decay. Okay, so now we've got our R, and we can come in and actually start working with this. We got our R from our half-life. So now we're going to come back in. There's our ratio. So we're going to have 0.65. That's how much is left. Is going to equal to e to the negative 0.00012 T. I just plugged my R back in up here. I think that's what I put down here. Yeah. There's the R I had, and I just plugged it into my formula. Okay, we need to solve. We're at base E. It's isolated. So I'm going to have natural log of 0.65 equal natural log of e to the negative 0.00012 t, or natural log of 0.65 equals negative 0.00012 t. Divide by negative 0.0012 t, or negative 0.00012. So it's going to be the natural log of 0.65 negative divided by 0.00012. And it worked out to be approximately 2,560 years was our age. Excuse me, 3,560 years. Okay, let's look at a couple of different examples. These are things you guys see or hear about pretty much every day. So first let's talk about a decibel scale. This is how sound is measured. This is how sound is measured. It is in decibels. However, this is a log scale, not a linear scale. And decibels are defined in this way. B equals 10 times the log, remember this is log base 10, of the intensity of your sound divided by I sub 0, which is the lowest intensity the average person can get. And I sub 0 is usually 10 to the negative 12 watts per meter squared. And this is how we define decibels, sound levels. Now, when B gets to be around 130 decibels, and the deci comes from multiplying by 10. It was originally just called bells, and they realized that we really need to multiply by 10. But B equals 130, you start hearing damage. Okay, when I was your age, a very popular rock group called The Who. And at their live concerts, they tended to have a decibel level of around 100 decibels. So you can see they were getting really close to this. Jet engines are around 120 decibels. And prolonged exposure, even at these levels, can start to cause hearing loss. The average for earbuds in adolescence, which is you guys, is between 125 to 135 decibels. You guys are going to be deaf when you get to be my age. You think I'm hard of hearing, you're really going to be in deep trouble. Okay, so let's take a look at how this works. So let's take a look at The Who. We know they were at 100. Okay, and let's take a look at what their intensity would be. So that's going to be 10 times the log of the intensity of The Who divided by 10 to the negative 12th, which is the lowest decibel I'm dealing with. Okay, I'm going to divide by 10. So 10 would be equal to log of IW over 10 to the negative 12th. So I'm going to raise this to the 10. So I'm going to have 10 to the 10th equal 10 to the log of IW divided by 10 to the negative 12th. Or 10 to the 10th will be equal to IW. Because this is 10 to the negative 12th, it's negative. I'm going to multiply it up here times 10 to the 12th. And I want to solve for the intensity of The Who, so I'm going to divide by 10 to the 12th. So I'm going to have 10 to the 10th divided by 10 to the 12th equals The Who, or their intensity was around 10 to the negative 2. This is in watts per meter squared, or about 1/100th of a watt per meter squared. This is the intensity of sound hitting your eardrum. Okay, so that's the Who. Let's take a look at a jet engine, which is 120. And that's going to be 10 times the log of the intensity of a jet engine divided by 10 to the negative 12. We go through the same process. End up with 10 to the 12 will be equal to intensity of the jet engine times 10 to the 12. So I'm going to divide through, so I end up with 10 to the 12 over 10 to the 12 equals intensity of a jet engine, or the intensity of the jet engine is about 1 watt per meter squared. So what you notice is an intensity gain of 20 decibels. We go from 1/100th of a watt per meter squared to 1. So an increase of 20 decibels is an increase of 100-fold in the intensity. Now, let's take a look at what you're doing to your eardrums. And let's just say we're dealing with 130. Okay, and that's going to be 10 times the log of intensity of earbuds over 10 to the negative 12. 13 equals log of I sub b times 10 to the negative 12. So I've got 10 to the 13th will be equal to I sub b times 10 to the 12th. Divide by 10 to the 12th. Or is 10. So you guys with your earbuds now are going up by 1,000 times what we did to our ears with the Who. Okay, another example, and it works very similarly, is a Richter scale. When you go in at that, the Richter scale, which measures earthquake intensity, is defined very similarly to this, only there it measures earthquake intensity, but it also deals with a log. So it's when you go up by a certain amount, you go up by tenfold in the intensity of the earthquake.